Hello, this is Fatih, the Associate Professor at Ozyegin University in Istanbul, Turkey. So I'm going to be explaining you the basics of very simple CPU in this presentation. With very simple CPU, I intend to make CPU design a simple task. Very simple CPU is not only simple in terms of its design, it's also simple in terms of its instruction set. It only has 8 instructions. So like any other CPU, a very simple CPU has core and memory. So the core basically goes to memory, fetches an instruction, looks at what the instruction is, and executes the instruction. And in order to execute the instruction, it may have to go to memory again and fetch data. And as a result of the instruction, it may have to go to memory one more time, write the result of the instruction, then go to memory again and fetch the next instruction. Very simple CPU is von Neumann. In von Neumann, program and data are in the same memory space. In Harvard architecture, however, there are two different memory spaces, one for program, one for data. We have a very minimalist approach and very bottom-up approach in very simple CPU, although it's not as bottom-up as NAND to Tetris, but still our philosophy is pretty similar. You may say, what is this CPU useful for? Because it doesn't have any inputs and outputs. This is like the fundamental architecture of the CPU. Through the concept of, through the idea of memory mapped I/O, we can easily add input and output pins to a very simple CPU. So this concept of memory mapped I/O has not been invented with very simple CPU. It's been there for forever. So no need to design a brand new CPU when you have a different pinout. A different pinout simply requires a different memory map. And a different memory map requires you not to change the core, the logic core. It only requires you to redo the memory. The memory still has the same generic interface to the core. The only thing you change in the memory is the memory decoder. Basically, the memory map is the table. It's basically a table of addresses. It's implemented in the decoder. The decoder grabs the request, read or write, to a certain address from the core and routes it to the pins or the actual memory inside this virtual memory. So very simple CPU, like any other CPU, thinks that it talks over a generic memory interface, which it does, but it thinks that it talks to the memory directly, but the fact is that it's talking to the decoder, and the decoder can access the pins. So every pin will have a particular address. An input pin could be at address 100. This input pin could be at address 200. This output pin could be at address 300. This output pin could be at address 1000. Like any other CPU, very simple CPU has an add instruction. So let's see what goes on with these instructions and what an instruction means. Every instruction is stored as a word in the memory. The very first thing the CPU, the core does, as soon as it's powered up and the reset is released, it goes to address 0 and grabs the first instruction. And let's suppose that the very first instruction is add 100, 200. Add 100, 200 means actually go to addresses 100 and 200, grab the data there, the two pieces of data, and add them up and write it back to address 100. So it means really star 100 equals star 100 plus star 2. Okay, let's see. Again, so add 100, 200. We're not really adding number 100 with number 200, so the result is not 300. Add 100, 200 means add the numbers in addresses 100 and 200 and write the result back into address 100. So what the CPU is supposed to do, let's say the CPU powers up, goes to address 0, so reads the first instruction, which is add 100, 200. By the way, I mean, it really doesn't have character A, character D, space, and so on in that location. Add 100, 200 is the readable version of the instruction. The actual instruction in there is a binary number, bunch of zeros and ones. The relationship between the binary numbers, the actual instruction, and this readable version of it, we call this assembly language. I'll explain you the relationship later on. Just bear with me for now. So the CPU, when it powers up, goes to address 0. So sends 0 as address to memory, and the memory returns it the contents of address 0, which is this add 100, 200. So in the core of the CPU, there is logic, there is intelligence, which lets it analyze the instruction. So it says this is an add instruction, and there are two addresses that come with it, address 100 and 200. Since add instruction is star of the first address plus star of the second address, it needs to go to those addresses and read the data there. So the CPU, first thing it did was sent 0 as address to the memory. Memory returned it the instruction at address 0, the contents of address 0. It analyzed it and decided that it needs to now go to address 100, meaning the core sends 100 through the address wires to the memory, and the memory returns the contents of location, meaning address 100, which is 3. So the CPU now has 3. It stores 3 in its internal temporary memory storage. Then it sends 200 as the address to the memory. It says, I want to access your location address 200. So the memory sends the contents of location, meaning address 200, which is 5. So it also stores 5 somewhere in its few handful temporary memory locations. Then it adds these two stored numbers, 3 and 5, and finds 8, and stores 8 back into memory at address location 100. So sends 100 through the address wires to memory, and then sends 8 and says to memory, I want to write you, I don't want to read you. So the memory changes the contents of, modifies the contents of location 100, makes it 8. So this is how it looks, how the memory looks before the instruction, the very first instruction, address 0, executes, and this is how it looks like after it executes. So let's look at a second instruction. Since the memory starts from address 0, the first instruction is at address 0, and the second instruction is address 1. 1 colon means the address is 1, and the instruction at address 1 is add little I 200, 100. Pretty much every instruction, most instructions, so very simple CPU, just like several other CPUs, they have their immediate versions. The little I means immediate here, meaning the second number 100 here is not an address, it's immediately the value itself. So if it's an add I instruction, it's not star the first number plus star the second number, it's star the first number plus the second number. So here we are not adding the numbers in location 200 and 100 and writing it to location 200. We're adding the data in location 200 with number 100 and writing it to location 200. So in 200 we have 5 still. We add 100 to it, so 105, we have to write it back to 200. So after the second instruction, meaning instruction in address location 1, we have 105, 105 in location 200. So here I want to also show you the actual instructions. So add 100, 200 is the readable version of it, is the assembly version of it. The actual instruction is a binary number. In the case of very simple CPU, every instruction is 32 bits. But these 32 bits have 4 parts. The leftmost part is the opcode. It's 3 bits because we have 8 instructions. The 4th bit from the MSB from the left is it's a single bit quantity. If it's 0, it's a regular add instruction. If it's a 1, it's an add I. Then the remaining 28 bits, half and half, 14 bits and 14 bits, it's A and B. So the 100 is the A argument, A part of the instruction, and 200 is the B part. Each are 14 bits. So in this particular instruction, we have to write 100 in 14 bits as a 14-bit binary number and 200 the same way. And this is how they are written in 14 bits, 100 and 200. So 14 bits A, 14 bits B, that makes 28 bits. 1 bit immediate, 29 bits. 3-bit opcode, 32 bits. Every instruction is a 32-bit binary number. Now, let me show you the other instructions, the ones other than add, NAND, SRL, shift right or left, less than, CP is copy, CP uppercase I is copy indirect, BZJ is branch on 0 or jump, multiply is optional, multiply can be done in a subroutine using add, shift and looping. Add, NAND, SRL, less than, and multiply are similar instructions. It's the same concept. Star A is put into an operation with star B and written into star A. The operation between them is add if it's the add instruction. It's NAND if it's a bitwise NAND instruction. I mean, it's bitwise NAND if it's a NAND instruction. And it's a shift right or left operation between star A and star B if it's an SRL, and so on and so on. The three remaining instructions are slightly different: CP, CPI, and BZJ. CP A, B goes to location B, grabs star B, and writes it into location A. So it's star A equals star B. There is no arithmetic operation. CP uppercase I does star star B, which is it goes to location B, gets the data there, treats it as an address, treats it as a pointer, goes to memory again, hence gets star star B and writes it into location A, meaning star A equals star star B. In this table, I use the assign symbol, an arrow instead of A, instead of equal, because when you say A equals B in a programming language, it's really not equal, it's assign. Every instruction has the immediate version. So here, little I, immediate flag in the binary version of the instruction. If it's 0, it's the regular instruction add. If immediate field in the 32 bits, somewhere here, is 1, it's the immediate version of add, which is add little I. That's the mnemonic of add immediate. Regular add symbol, abbreviation, short name, also called mnemonic, is add, and add immediate is add little I, which means the immediate flag in the binary version of the instruction is 1. So add little I, NAND little I, SRL little I, less than little I, CP little I, CP uppercase I little I, BZJ little I, multiply little I. So SRL is shift right or left. If star B is less than 32, it's shift right. If it's 32 or more, it's shift left. If in all cases, if it matched shift right, it would have been meaningless, because if star B is 32 or 32, or let's say 33, shifting a 32-bit number, all our data, instructions, everything is 32 bits, because our memory is 32-bit wide. If we're shifting a 32-bit data to the right by 33 bits, for example, it will become 0, so it's meaningless. So any shift amount, star B, that's larger than 32 or equal to 32, means it's a shift left. So a shift by 32 is not a shift right, it's a shift left by 0. A shift amount of 33 minus 32 is 1, so it's a shift left by 1. Okay, the little I version doesn't grab the shift amount from star B, it grabs it from B. By the way, when I say star B or star A, I don't again mean A or B, the values themselves. It's the values in those locations. So star A, star B, star meaning indirect referencing or pointer mechanism. Using star for that mechanism is a syntax used in C language. I'm familiar with C, but I presume if there are other languages like C which can deal with pointers, star A, star B would mean the same thing. So BZJ, regular BZJ, meaning immediate field is 0. BZJ little I, meaning immediate field is 1. So this is what they do. BZJ means branch on 0 or jump. The regular one with little I 0 is actually BZ. BZJ little I is really J, jump. So jump is an unconditional branch. A branch is a conditional branch. And the condition is star B. If star B is 0, we jump. We jump to the location in A, hence PC equals star A. PC is, by the way, means program counter. It's the address where we grab our next instruction from. Normally, our next instruction will be grabbed from the next location. Hence, if it's not 0 in star B, we will do PC plus plus PC equals PC plus 1. In the case of jump, it's not conditional. We don't look at a condition. We change PC to star A plus B. So this is it for now. Talk to you later.